So if you are here in this webinar, it's probably because you already know about Rust, but just in case, I will give you a very brief overview of the language and the reasons why people think about using it. So first, Rust was designed from the beginning for the safety critical market and for the to have high performances. It's a language which has safety-oriented features such as type safety and notably memory safety. It has embedded support for concurrent and parallel programming that allows you to do that and preserve the memory safety that is behind the Rust idea. And it's a language without garbage collecting, without things that could have a bad impact in terms of performance. So that is, let's say, a very quick introduction to the technical part of Rust. But there is something in the Rust language that is very, very powerful, which is the community. The language has been ranked as the most loved language for a few years already. And there is a very, very enthusiastic community behind Rust that makes the language very much alive, very much used, and people trying to push that language everywhere. And it's typically easy to adopt for people with an understanding and knowledge, a certain degree of knowledge of, say, C or C++. I will not go much into the details, but I wanted to mention a bit about memory safety, which is probably the biggest technical asset of the language. So the idea is that you want to prevent any sources of undefined behavior. Undefined behavior is very tricky thing because it has typically very bad effect, and it is difficult to debug. It's difficult to go look for the source of the problem. So the language, as I said, comes with strong data typing. On top of that, it adds very tight lifetime rules so that you typically prevent accessing to data, to objects that may already have disappeared. And as I said, there is in the language there are primitives to ensure that if you access to shared data from different concurrent entities, there is support to prevent data races. One of the things they have is runtime. There is a lot that is checked at compilation time. When you compile, the compiler will say, "Oh, this that you try to do is not safe, so I will not allow you to do that." But there is also some things that are checked at runtime, like what you are seeing on the top right side, which is array indexing. If you try to access an object from within an array, there is a runtime check to make sure that you are trying to use something that is already within the bounds of the array. There's a mechanism to handle storage overlaying in a safe manner. This is for those that know a bit of Rust, this is the enum type. And there is basically there is a tag associated to the object to know what we are talking about and to know what are the different fields that we can access. And that again comes with runtime checks to make sure that we are not using the wrong thing. Obviously, if I talked about pointers, this is probably where Rust shines the most. And with its ownership model and lifetime management, the main idea behind Rust is to make a safe use of pointers and to ensure that there is all the references that are used are valid at any point in time. And then there is some concurrency protections to ensure that even if you try to access a given object from different places, you still keep the consistency in place. A word about memory safety again. There's been a lot being told about memory safety and memory safe languages, and in the US there have been a few documents that were issued to try to move away from non-memory safe languages and push the use of languages that come with memory safety in the model. So that is one of the reasons why we keep hearing about Rust and why people try to push Rust these days. Now, I will tell you a bit about our Rust offering very quickly. The idea behind our compiler for Rust, GNAT Pro for Rust, is to use what we have learned in the safety critical industry for 30 years with other languages like Ada, C, C++, but to do that on Rust. And I will give you a bit more detail, but the idea is to be able to have good support on the language and on the tooling, have long-term support on the tooling, being able to use the tools for decades if needed, because this is the situation that we see in our market. People need to use the tools in a safe way for a very long time, and that's why we provide you every year with an updated version of the Rust tooling and language that we can keep alive for more than a year, of course, but we provide a new release every year. We build it with our system where we know very well the dependencies and the elements that are used to build your tooling, and we can also provide you with an SBOM, a software bill of material, where the pedigree of the different components that we put into your tooling, and all that with the capability of backporting critical fixes. If we release the tool today, and in 6 months we find a critical problem that needs to be fixed, we can do it for you. In terms of elements, what you get when you unbox our GNAT Pro for Rust, you get basically what you would expect. The tools, you have the Rust C compiler, that in this case, for example, we found it was the release, the 25 release was based on Rust version 177, but we added, there was a critical bug that was found, and we backported that fix to our compiler. Obviously, you have the cargo builder, the debugger. GPR build is our own tool to facilitate the building multi-language applications. Linters such as Clippy, formatter Rust FMT, and the IDE support via Rust Analyzer. And obviously, Rust is of small use if you don't have libraries. You need almost every time you need libcore at least. So we provide a set of libraries that you can use in your development, like libcore, of course, libstd for it's either full for the native ports of a small subset of it in embedded or bare metal targets, leave a log for memory allocation, libraries for macros, and for testing. So that's typically what you would expect in your Rust tooling. How obviously you are probably very familiar with the open source Rust that exists, and I'll go into a bit of differences between that and the compiler, the GNAT Pro for Rust that we provide. On the open source side, you basically you invoke a kind of magical script that will install the tooling somewhere and will set the paths that are needed. So it's a bit, it does a lot of things behind your back, I would say. If you go to our tooling, you will basically download a concrete package that will contain everything, and you will install that tool wherever you want. So you have a much more control over what and where things are installed. But once you do that, once you do that installation using open source Rust, or our GNAT Pro for Rust is transparent. The same commands that to build to run your application will work exactly the same when using the GNAT Pro for Rust. And now I think one of the things I wanted to mention is what is needed in the safety critical industry to adopt Rust. And we at AdaCore, we worked a lot on that, and we made 3 different groups of things that need to be done or achieved. First, you need to know that you have the appropriate tool chain, and we will see details in a moment. Then you will need to have the appropriate support to use these tools. And then if you go, and you will typically go if you are doing safety critical development, if you need to go through certification, you need to have everything that is needed to prove compliance against these standards. So first, let's see what we offer with respect. I will show a comparison between open source Rust and our GNAT Pro for Rust. Doesn't mean that they are completely different. Our GNAT Pro for Rust is based on upstream Rust, but the difference is how we manage this tooling. For example, here one of an interesting example is that the Rust tooling, there is a new release every 6 weeks in the open source community, which is nice if you want to be up to date and follow the latest development in Rust. But if you are doing an industrial project with safety critical constraints, this is probably not what you want. What you probably want is to have something stable that you fix today, and somebody able to say, okay, use this compiler, and whenever we find, or you find, a problem in that compiler, we will fix it, but the rest will remain the same. And that will give you a lot of stability when you build your application. Obviously, there is a question about targets. What targets are you interested in? The open source Rust, there is interest in basically native targets and some embedded targets. For our customers, we do support the targets that they need. For example, obviously we support the native targets, but we support things that our customers ask for, like VxWorks or some bare metal targets, or even a specific port for their specific platform. And then you have the integrity of what we provide. When you get our support, you are sure that you will have answers to your questions, and you are sure that we can tell you what makes up your tools. We can tell you how we build our tooling. If we go into support, I think one of the main thing is to be able to to fix the version that you want to use. The moment you start your project, you can say, I want to support this version of the tools for a number of years, and we are able to do that for you, and we are able to upgrade that tooling for you, but just to fix potential problems, but not affecting, for example, the version of the Rust language that is supported. So you have an assurance that if you upgrade the tool with all these safety critical patches, anything that compiled yesterday will compile today. Again, if you get the open source Rust, you may ask questions, and you may or may not get answers to that. On our side, if you ask something, we provide you a guarantee that within 2 days you will have an answer for us. We will be able to manage even ITAR material if needed, and you will get support. You will get answers from the people working with in the production of this tool change, and you will be informed on where the different problems will be fixed, and what is the package that you need to get in order to get the fixes that you want. And finally, if you ever need to go through certification, probably not because this is what you like to do, but because you are forced to, we can help you in that, because we have a very long experience doing certification and qualification for Ada, C, C++ for different certification environments, and that is the thing that we are doing for Rust. For example, on the tool chain part, we can qualify the builder, cargo, the compiler, Rust, and the linker. But obviously, the runtimes the libraries will be embedded into your final application. We can provide you with the certification material that is associated to the libraries that you use. Typically, you will probably need a very big part of the liballoc and libcore that we can certify for you, and potentially you may want to have to use a part of the libstd to do your development. We can certify that part for you based on our experience doing runtime certifications for other languages and for many different certification standards. But so we have talked about the tools to generate your executable. We have talked about the libraries that you will embed within your final executable. These are things that are needed, but you also need some tools to do analysis to verify the application that you build, and that typically covers two main things. Code coverage analysis tool. You will need to ensure a certain degree of code coverage, and you will have to ensure the adherence to a coding standard. These are things that we are again working on, and that is something that is that we plan to provide within our. We have already tools doing that for Ada, C, and C++, and we are working on extending that for Rust and qualify them. I don't think we will need to go much into the details here, but just for mention, what we provide you is a stable tool chain with a pedigree that is checked by us, and we follow it to check whether there are safety critical fixes that need to be integrated. We have a set of experts that will give you the support that you need around the tooling and the language. We are able to do with you a long-term support agreement by which you can use a given version of the tooling with critical fixes for as long as needed. We will support the target platform that you need, and we will help you doing incremental adoption of Rust. There is not a lot of people that will start everything from scratch in Rust. Typically, what you have is an existing code base, for example, in C, and you want to replace a part of it with Rust. We will help you build this multi-language application. So with that, I will leave you in the capable hands of Antoine.
Thank you, Jose. Thank you very much for that good introduction on Rust, and a lot of very interesting information there. So I'm going to give you a little bit of an intro on RVS, one of our product, and how we do support Rust in this product. So just to start with a general introduction to the Rapita Verification Suite, which is one of the product of Rapita Systems, which is a suite of verification tool for various aspects of software verification. So we've got in the suite, we've got a testing tool called Rapitest, which you can use for doing your software tool testing, which can be done at system level, integration testing, or unit testing level. So this is a tool which allows pretty much to test the code as it is without having to introduce anything which is specific for testing. It generates all the framework, all the extra accesses that you would need for testing your code. The other one, RapidCover, which is a structural code coverage tool for the usual metrics from function level coverage, statement, decision, up to MCDC for DAL-A systems in DO-178, and RapidTime and RapidTask, which are both timing analysis tools. So RapidTime, which is your single task, single thread timing analysis, or worst case timing analysis, where the goal there is to understand the timing of a single task to check that deadlines are going to be met, and RapidTask, which is more of a system level, understanding the scheduling and detecting errors or problems that could arise between different threads and different tasks, which are all scheduled by an OS typically. So the focus of RVS is very, very much anything which is to do with critical embedded systems. That's the main focus of this set of tools, to provide a very good and efficient way of performing the verification of these critical embedded systems. We specialize in on-target testing, which means that all the tools and methods are optimized to run on the real hardware as close as possible to the final target, which is recommended in many of the. I seem to have lost the screen a little bit there. Recommended in a lot of the way you should be certifying your systems. The closer to the end target, better. And all the tools are qualifiable, so we do have qualification kit for DO-178 and ISO 26262. So that's obviously something that is required if you need to perform verification for, again, these standards. So going a little bit more into detail of the tools. So as I said, there are different, so the RVS, so the verification suite is made of several plugins. So typically, users will be using one or several of these plugins. We have two flavors of some of the plugins. We've got the normal version, which is, I would say, the version where you will perform the analysis at the source code level. Typically, that would entail some instrumentation of the source code. And there is a version where you can do it at the object code level, where no modification of the object code is required. In some cases, you don't even need to have access to the source code, so that might be very useful if you need to do some analysis on libraries for which you don't have the full code. Now, this does require a lot more hardware support, so there are some constraints, but it does give you a very, very precise level of information on the object code, which is also mapped to the source code, if possible. So I'm going to concentrate in this talk and this demo later on the Rapid Time Zero and how Rapid Time Zero supports your Rust verification. So let's have a look in detail about what Rapid Time Zero is about. Oh, before that, yes, so just a quick mapping between the type of objective that you would have to fulfill as part of your verification of your onboard software for DO-178C. So rapid test typically used for your requirement-based testing methods. So can be high level or low level, or any level requirement which you can verify through software to software testing. Rapid Cover Zero are going to be used to fulfill the 6442 structural coverage objective. Rapid Cover Zero can also be used to help verifying the source code to object code mapping requirements, which is a way to check that no extra code has been introduced by the compiler that you can't trace back to your source code in the first place. And then there's a lot of objectives to do with time analysis as well that can be fulfilled by a combination of rapid time, rapid task, and the zero flavors of these tools. So let's go look in detail at Rapid Time Zero and the Rust support of that tool. So first question, what is Rapid Time Zero? So Rapid Time Zero is our timing analysis solution. It automates a large part of the work required to perform time analysis on software. This version, because it's a zero tool, works primarily on object code level and supports Ada, C, C++, and Rust. Technically, it also supports other languages which compile to object code, but there are some specificity to the in the support of the Ada, C, C++, and Rust language, which makes the tool give you better information in terms of object code to source code mapping for these languages. One of the important factors that Jose mentioned earlier is that we do support mixed language software. So it's very, very often that you will find that maybe you are starting using Rust, you are not going to write your entire software in Rust. You're going to have maybe a couple of libraries in Rust, and the rest is going to be either legacy code that could be C, C++, or Ada, or high level. Certain components could be written in Ada, certain components could be written in Rust. It's important to have a set of tooling that will allow you to perform a verification for this mixed language and produce a unified view of the software and the verification results across the different languages. So what do you use Rapid Time Zero for? So this zero footprint time analysis is the main reason why you would use the zero flavor of Rapid Time. You don't need to have access to the source code. You don't need to instrument. Now, obviously, if you do have access to the source code, it's going to make it easier to understand the results. You still do not need to instrument that source code. So the source code is very, very much an optional piece of data, which is definitely a plus if you have it, but it's not required anymore. You don't need any modification to your development environment. We are purely working on the end result of your build system, which is your object code. So you can be pretty sure that you are going to perform the analysis on the final artifact, the software as it is about to fly or run or whatever. There's no question about discrepancy between the software and the test and the final software. The timing results are not simulated, they are not estimated, they are derived from actual measurements. That's where the hardware solutions, the hardware requirements are a bit higher than normal. You need to have a hardware tracing facility that lets you obtain these actual, very precise measurements of your system on the real target. And one of the aspects of why you would use Raptime Zero, obviously you can use it for your final verification to make sure that your software is going to meet the deadlines which have been and the time and budget which have been allocated for various tasks. But another thing which is basically trying to optimize the efforts, to guide the optimization efforts. So to make sure that if you are going to spend time refactoring, improving your software, you spend the effort where it counts in terms of where the worst case execution time is going to be, and not in places where it doesn't really matter whether the software can be 5% faster. It's not going to change the total budget requirement. So various use cases for Raptime Zero. The first one, understanding what's going on in terms of timing behavior. Again, you don't need two instruments. You can very, very quickly deploy this solution. You don't have to have prepared the software specifically for timing analysis. You can take any build of your software and run timing analysis on it. The next one is towards the end, toward more your as a certification evidence, you will need to demonstrate that your software executes within the time constraint. So that's something that you can do with using the worst case execution time calculated by Raptime. A typical use as well is to upgrade legacy system, just to figure out, okay, is there enough room in the schedule, and can we update part of the system by adding functionalities, new features, and making sure that we still meet the timing budget that was set before. Another one, which is making sure that your software is safe and predictable. So that does help a lot in terms of the style of coding and the type of design as well. There's a lot of ways of writing same algorithms, some which are going to be more time predictable than others. You can spot parts of the software which are not very predictable, where there's a lot of variability of execution time, for example, which is not a good property of safety critical software. As I say, addressing the various DO-178 guidelines is another use case. And finally, if you do want to do timing analysis on software which is either entirely or partly written in Rust, this is also a very good use case for using Raptime Zero, which is going to give you the same information whether your code is Ada, C++, or Rust. So what does this tool produce in terms of metrics? So there's quite a few things which are going to be produced in a report. I'm going to show you an example of such a report very soon. So we will be showing a set of measured metrics, like the overall execution time, the average execution time at various levels, at the function or subprogram level, or even more detailed than that inside each subprogram. There will be a notion of high watermark, which is the information, the timing information that have been captured during the longest run of your system. So that's an interesting case where, typically where you would have tests which have been designed to maximize the system. So you would want to capture high watermark, and you want to be able to see if you can capture, make your system perform its worst execution time behavior during that test. So all these three are measured metrics. The last one, the worst case execution time, is actually an analytical metric. So it is not something that is purely measured. This is something which is going to give you a picture of what could happen if your test were to exercise your system in a slightly worse case than what you've captured so far. So this is where the tool is going to use information about what is possible in terms of execution paths in your software, and also what has been observed on the various execution paths, and start building a picture of something that could happen that you might not have tested yet, but that the software does allow or would allow to happen. So it's going to give you information about maybe how to improve your maximizing time testing, so trying to get better timing, or also give you some higher bounds, basically what your budget should be. And then you've got the detail of the contribution of every function in the software towards the overall execution time, be it measured or worst case. So that's a very useful metric to decide which part of the software you need to optimize if you've got issues with budgets being too tight, for example. So it's not going to give you just information about which part of software takes the longest, but also which one contributes, because you could have a very, very small part of software which is executed millions of times, and that has a very, very high contribution. I'll give an example in the demonstration a bit later. So mixed language integration. So as I said earlier, the verification can be performed on software which is written in a mix of language. So you could have a main task which is written in Ada, then some algorithm which are called from there written in Rust, and then maybe the Rust itself is going to call some library functions which are still written in C or C++. All of these can be presented in a single report and analyzed as one unit. So as I say, the entire build and verification workflow can be completely unified. Our tool integrates already with the GNAT Pro for Rust tooling, specifically the GPR build tool, which is a tool that facilitates these cross-language build systems. And information, the timing information flows across language boundaries. There's no limit. With as you'll see in the demo in a few minutes, you will see the detail of timing being spent from one language to the other completely seamlessly. So looking ahead, where we're taking RVS. So we do see that modern language like Rust has a potential future for safety critical software. That is definitely a language that seems to be getting a lot of traction. There's lots, as Jose said, there's a lot of emphasis on the security and safety aspect of this language, which makes it a very, very good candidate for the safety critical environment. And we want to be there to enable the adoption of this language in maybe first a mixed language environment by providing tool support in this environment. Another aspect where we're taking RVS and the rest of tooling, we are looking more and more in supporting multi-core systems. Again, you could have a multi-core system where some tasks will be developed in Rust, some tasks will be developed in Ada. I'd say a lot of this is made possible by relatively quite close partnership with AdaCore and really understanding where they are going with their support for language themselves. So tool demo. So I'm going to give you a quick demo of some data that has been produced by Rapid Zero. So this particular demo is based on the GNAT Pro for Rust tool chain, which has been used to build a mixed language Ada and Rust application. So it's an example application, and this has actually been run on a Xilinx ZCU102 board. And we've collected the information, the data, let's say, the timing data, using a Lauterbach debugger, so which is one of the methods that can be used for obtaining fine timing data from a hardware like this one. Very good. So I'm going to attempt to share my screen now. Hopefully, right. That's the point. Maybe I'm going to need some tech update because I don't seem to have an option to share my screen in this setup. Don't know if Oli is there, can enable something. There might be some bit of configuration that needs to be done to turn the screen sharing on. Right, that's okay. That's appeared now. All right, so you should see my screen. Everything seems to be working well. Good. So this is the main page of the RVS toolsets. The first thing we're going to do, we're going to open a report which has been produced recently, as I said, on this board using the ZC102 and the Lauterbach debugger. And the first thing we're going to see here is that we have indeed a mix of Rust code. So we've got a few example functions performing various activities. We've got Monte Carlo algorithm and things like that. And we have one Ada file, which turns out to be our top level function here. So the first thing I'm going to show is, well, I can show some source code to start with. So I don't know, for example, this, I can open the file. Let's try again. View source code. Yeah, that's better. Right, so we have some Rust code in here and then some Ada code in here. Remove the colors for now. So a very, very simple test program. We have one Ada function, which we can visualize as object code or as Ada, and it's calling quite a few functions. All of these happen to be Rust functions, testing various aspects of the tooling. Very good. So that's the first view of the tool. So going back to the top, I can see the full call tree of my software here. So as a reminder, this function there, this is an Ada function, and all of these underneath are Rust functions. So let's have a look at the execution time for this top function, for example. So I'm opening the detailed information for the top function, which is external library intensive. And here I'm going to see the various metrics represented in various ways. So on this bar chart, I can see that the worst case, which is the analytical worst case, which has been computed as a possible outcome of running that software, compared to the maximum observed. So I can see I've got quite a bit of difference between these two, meaning that potentially I could improve my testing of the software to increase the maximum observed to something which is closer to the potential worst case. So the maximum and the high water mark are the same, similar. The average is quite a lot smaller than the maximum observed, and then the minimum, it's not too far from the average. So it shows me that this piece of software seems to have a lot of variability between its average, minimum, and maximum, which is not a great thing for having something which is very, very predictable and deterministic in terms of its execution time. So having a look at the detail, I can see that my minimum there is in microseconds. So I'm going to have lots of information about the various timing aspects of this function. There's lots of detail as well of all the functions which are being called as part of the first of the top function. I can see more details about things like, for example, the contribution time. So, for example, let's have a look at the high-level contributors for this software. So I'm going to move to the top of the report, and I'm going to sort things by, let's say, the worst case contribution. So in here, I can see I've got two big contributors. I've got this function there, which is 590 microseconds, and has a contribution of ×1. So this happens to be called only once during an invocation of my task, but has high contribution. And this is much smaller function, but because it can be called 2,000 times per invocation, its contribution is also quite high. So that's an example of why it's important to have both numbers to understand where to optimize. Now, maybe an optimization in this function here is going to have a much bigger impact because it is called 2,000 times. All right, so other things that you will find, need to be able to access the other tabs. So we have dependency tabs, again, going to show you the links between the various, in this case, functions. So you would have information about coverage of your code, because in order to get good timing information, we need to have a good coverage of the code. You've got information about the invocation of various functions. So, for example, I can have a look at the GCAS function in there and see that, again, this one is not very, very predictable. And then going back to the detailed data, if you want to see exactly where this time is spent on the code, you can view your code at the same time as your test data. I can have a look at, for example, the coverage information of this function there. So this particular function has got very, very good coverage. I'm going to go to another one which has slightly worse coverage. So this one's not very good coverage. I can see in detail where this lack of coverage or these coverage holes are going to be. So, and I'm going to see all this information being coverage or the worst case pass or high watermark pass. All of this is always going to be shown both in terms of your source code, which is in this case Rust, and also the object code that corresponds to it with a mapping from one to the other. So whenever something might be a bit difficult to understand in terms of the object code, you've got the source code there, which is optional. If you don't have it, you can still perform the analysis purely on the object code. But if you do have it, it gives you a nice mapping to be able to understand a little bit better what your object code means in terms of the source code. All right, very good. So I'm going to leave the demo as it is so that we've got some time for Q&A as well.
Thank you, Antoine, and thank you, Jose, for your presentations today. Before I move on to the Q&A section, I just wanted to mention that both AdaCore and Rapita Systems will be exhibiting at the High Integrity Software Conference, which is taking place in Wales on the 13th of November. So if you want to speak to people about Rust or embedded software, aerospace, avionics, then that's a good exhibition to attend. So hopefully we'll see you there. As promised, we'll move on to the live Q&A section. Thanks everyone who supplied questions. I'll try and get through as many as possible in the next 9 minutes that we have. If we don't get to your question today, we will try and answer them via email. So looking at our first question from Ahmed, he said, what's the rate of adoption of Rust in the critical embedded industry, aerospace, medical devices, etc.? Who would like to pick that up?
I can give my part of it, and I can let Antoine complement that if he wants. So I have a rather good view on the aerospace industry. And what happens there is that there is a lot of interest in Rust. There's a lot of people wanting to do things. And there is a lot of prototyping or proof of concept. But there is what I'm perceiving is that nobody wants to be the first going into certification. So they are trying to delay the industrial usage of Rust until there is somebody else who is moving forward, or who is making good progress in certification. So there is a lot of usage, internal prototyping, proof of concept, but not much industrial embedded usage yet. That's my view.
Yeah, I agree with you there. There's definitely a lot of interest, and people want to see that the environment is going to be there before they commit completely to using the language in safety critical. But there's definitely a lot of excitement about it. I mean, it's the first time in a long time that a language seems like such a good candidate for that purpose. I think, and maybe people who've been around long enough remember the hype that was around real-time Java at the time, and we know where that ended up. So there's also some caution there, but it's definitely very interesting to see that everybody is talking about it.
Thank you. A question that probably follows on from that, and it may well have been answered, is there a safety critical subset of Rust for aerospace orientated certification, or is the whole language considered safe? Question for you, Jose, I think.
Yes, so that's an interesting question. There is a safety critical consortium for Rust, and this is one of the topics on which they are working. So they are working on the definition of a safety critical subset of Rust. It's in the works. It's not finalized yet, but there is a group of people working on it. So it will happen.
Thank you. A question from David. Does RVS provide a module for SEU, single event upsets, fault, rare event, bit flips, for example, due to memory corruptions?
So not directly. We don't have a module which is directly targeting that. Although the nature of the way RapidTime gets data and produce reports, meaning that we record everything. So it's not like a profiler that would be doing some sampling of your timing data. Everything, every data, every timing is being kept. If one of these single event upset had a timing effect, like having to do memory access a bit longer than usual, that would be captured in the timing data, and that would show in as an outlier on your software. You will see that for no understandable reason, a particular bit of code, which is normally like a few lines of code, which is normally very, very deterministic, will take a number of cycles more than usual, and typically that cannot be explained. And SEU might be one of the reasons why that's happening. But we don't have anything that specifically looks for them outside their impact on the timing of the software.
Thank you, Antoine. Another question. What's the learning curve for avionics engineers moving from Ada or C to Rust in real projects?
If I may answer that one, I think that learning Rust, I mean, what I've observed is that learning Rust is not difficult for people knowing already a language like C, C++, Ada. It's not that far. I mean, there is not a huge difference between both. So it's relatively easy and quick to catch up with Rust. Then obviously there is one thing is to be able to code in Rust. Another thing is to know everything and to know all the details of Rust and to know all the subtleties. That may take time, but new engineers can learn quickly, and if they are within a team where there is people able to help them for the more tricky questions, it's the adoption is relatively quick.
Thank you, Jose. I think another question for you is GNAT Pro for Rust? It uses yearly releases. How do you manage urgent security patches between cycles?
Yes, so we have a release cycle where we have the .0, .1, and .2 releases by default. So whenever we find these three are based on a common Rust version. So we take a fixed version from upstream of Rust, and then we build these three releases. The moment when we monitor how things go on that, either from the Rust community or our customers, if there is a need to a fix, we fix the version that we are about to produce. So if something happens when we are testing the .0 release, the fix will be introduced into the .1 and .2 releases, etc. If something happens after the last release, the .2, then we have the opportunity to create additional releases for people wanting to stay on long-term support. So by default, we would stop at the .2, and then the next fix will be in the next .0 release. But if you are in a long-term support, we will create a .3, .4, and any number that is needed.
Thank you, Jose. Probably time for one final question is, what's the biggest hurdle in convincing certification authorities to accept Rust for DO-178C compliance?
I think there are two things. The first thing is that it's simply that it's new. These authorities are they know how to deal with C++, ADA certification. They have done that for years. Rust is new, so they don't know how to. But they try to apply what they know from the other languages. But there is a degree of novelty that they don't know how to handle, and they will probably even more conscious about how to do this certification. So that is the one side. On the other side, there is also the lack of a very mature ecosystem. On C, ADA, C++, we have been doing coverage analysis for a long time. So for example, this coverage analysis tool are well known, are well understood, have been proved in many different projects. This is not the case on the Rust side. On the Rust side, all these tools are new, and they need to prove their pedigree. So I think these are the two main hurdles.
Would you like to add anything, Antoine?
Yeah, I think the familiarity and the knowledge as well as being accumulated on the other languages for many years. Anybody who's been using C++ came up with a set of coding guidelines where they only use a subset of C++. For ADA, people have been using Spark for a long time. So again, there's maybe not that consensus yet about whether the entirety of Rust is applicable, whether we should be using a subset of Rust, whether there's part of Rust which are better to not be used. So until that consensus comes out, I think people will still be asking questions about how are we supposed to be using this.